investigation of energy power parameters of thin sheets rolling to improve energy efficiency. Cold rolling significantly changes the properties of metals. With an increase in the amount of reduction, the yield strength of metal and the resistance to deformation increase, and the elongation of the strip decreases. This is due to a change in the grain size, which leads to a change in the structure of the metal. Also, an uneven distribution of friction forces occurs, which affect the deformation process. All these factors affect the change in energy consumption during rolling, which affects the cost of rolled products. The distribution of strains and stresses during cold rolling reduction is difficult to study under production conditions due to the very high cost experience. The study of cold rolling with the Deform 3D allows to significantly reduce the time for experiments, speed up the deformation of rational reduction modes during cold rolling. The results of these calculations will allow to develop measures that will make it possible to reduce energy costs, improve product quality, increase efficiency, and reduce the cost of the process. Purpose of work. To investigate cold rolling process of thin steel sheet using the Deform 3D software to determine energy power parameters of process. In order to reach this goal, following tasks were set. To create model of cold rolling of thin sheet, to determine force and torques that rise during formation process and their distribution in strain zone. The deformation scheme and the method of calculation of process parameters are present on this slide. We determined the deformation degree, absolute reduction, yield strength of material, rolling force, torque during cold rolling, rolling work. We also use dependencies that reflect the properties of material, such as stress strain, which shows value of stress at which plastic deformation of material begins, and heat capacity of steel and temperature, which shows that heat capacity of treated steel increases with increasing of temperature and takes maximum values at 210 degrees. This increase occurs under influence of plastic deformation. After this temperature, heat capacity decreases. First figure shows that maximum displacement vector appears under press of upper roll at beginning of treatment. Bottom roll has less intense impact on metal because top roll is the main tool. An area has also been identified that requires special attention in terms of possible cracking. Second figure shows that maximum strain values in strain zone reach 0.309 millimeters per 1 millimeters of workpiece height. Third figure shows that rolling force increases during the first 9 seconds and reach 5.5 meganewton. In real condition, for this model, the rolling forces reach 5.3 meganewtons, which corresponds to a high simulation accuracy, with the error is 5.5%. As you can see, the rolling force varies over time very evenly. This is explained by the fact that the rolling process is uneven because the amount of reduction can change due to the presence of various micro-roughness, both on the surface of material and on the roll. The simulation results were used for theoretical conditions of the work and the rolling process, the productivity of the process. The effective degree of deformation equals 70%, enabled to obtain sheets with maximum hardness, which can be plastically deformed. With increase of deformation degree, stress of metal surface layer increases, as well as force and torque. Micro cracks and microfibers may appear of sheets and rolling tools. Reduction of the deformation degree up to 45% leads to decrease of strength and hardness of metal. Sheets is able to deform plastically under load during operation. That's all. Thank you for attention.